I am Dr. Bilal Masud, and this is second video of this course on quantum mechanics. In the previous video, I introduced two questions, that if you have a measurement, and I showed measurement as dots. Two questions are, what are the properties of the dots, and what is the distribution of the dots, that where are dots more and where you have less dots. Now, for these two questions concerning these, if you know for some reason or other that the dots are produced by bullets, then bullets are daily life things, and that is where I started last video, that for daily life you can use classical mechanics, Newtonian physics, and that common sense physics will give you a result which will be verified. So that's for say for bullet. But if, as it is there in the next video and next to next, if the same experiment is repeated with electrons, and you tell where electrons more detected and where less number of dots using classical mechanics, then that will not be verified by experiment in today's time. Okay, means for electron or photon, as far as present physics is concerned. So present physics says that for electron or photons, if the dots are due to electron and photon, the distribution is necessarily to be told, as far as present physics is concerned, as long as it is there, that distribution must be given by quantum mechanics. And that is the topic of this course, that what quantum mechanics will do in this for this distribution. And the answer is the following: that quantum mechanics introduces a differential equation called wave equation, and the steps are simply you select wave equation, solve wave equation, find wave function. Step number 2, and square it to get probability density, integrate, get probability, and that probability is measurable quantity, and that scheme is completed. Is that complete quantum mechanics or not? That is some next discussion, not this video. But at least if it is complete, you should be able to discuss that. You should be familiarized to that scheme. You decide about that in next time. So if first you understand scheme, what it is. Now that scheme needs position dependence. I'm saying where dots are more, where dots are less. So that means that's a dependence on position. And if you represent by horizontal x, vertical y, that means the dots distribution physically the quantity becomes it's called probability density. Probability density as a function of x and y, and in general can be a function of t, time, but this picture is taken with a fixed time. So here you don't see time. So for one time is x or y dependence. Now dependence here means changes in x. Change becomes differential if the change is infinitesimal. Just learn the word differential, and differential above maybe above y, differential, and then maybe time differential. So you have to let differential. That's our mathematical problem, and that relation is called differential equation. Now to introduce you to what is the differential equations, I've chosen an example which is actually from physics, although the purpose presently is mathematics, but the physics example will maybe help you imagine more easily that where the differential, where changes originate from. Now to get that, you have to learn two kind of changes. One is the time change, that is introduced if you use Newton's second law, because that has acceleration, and acceleration whatever it is, that will induce double time change, that means second time derivative. Now as far as position is concerned, you have to better take a particular example. There is a string is there, an ordinary string that is vibrating and it's not in the equilibrium position. It's above its minimal length. If it is rubber or so, or maybe ordinary material as well, if it is vibrating, you can understand what is required. So you consider a portion of it and you apply Newton's second law. Newton's second law will say, as I said, mass into acceleration is net force, and net force is, if we are talking about vertical force, you have to take components of force. Now components means, here is a trigonometric sign. For small angle, that is approximately same as trigonometric tangent. And tangent is slope, and slope is a derivative, a rate of change, a ratio of changes. So that is slope is one derivative, and then because we are taking the changes from t1 to t2, that's another change. So it's a change of change, that is second position derivative. So we have so you know something which is called differential equation, and that was the immediate purpose, to learn what is called differential equation. Now in this differential you see that both respect to time, respect to position, you have second derivative, and second derivative, the solution could be trigonometric sine. You differentiate once, it becomes a cos, and then minus sine. The sine comes back, so that means sine. If you put sine here, both sides will become proportional to sine again, trigonometric sine, and the equation will be satisfied. And the same thing with e power iota, that will satisfy, you can put, and that is satisfied. So you learn this word solution of a differential equation, and if the differential equation is wave equation, the solution is wave function. In this small case, it's not a quantum mechanical wave function. The wave equation is classical, so it's a daily life ordinary string, it's a vibration. The solution, if it is time actually, now you consider time changing, then you can see its motion. Although time change is not immediate topic of this lecture, but at least maybe it's good to see that it's for next lecture or so. But that's the mathematics. Immediately go to the what's present topic is that we have to apply math to physics, and the physics is that if you see dots, measurements, as the topic I started today's lecture with. Now first you have to choose the differential equation, and this is this way. If dot has zero rest mass and zero electric charge, the terminology is, you would say the dots are due to photons. The photons are light waves, particles. Today we say quantum particle, and light waves are electromagnetic waves. Electromagnetic waves are Maxwell waves, you can say, that because Maxwell summarized and then extended equations for electromagnetism, which included prediction for electromagnetic waves. Now if distribution is, position dependence is of dots due to photon, the differential equation would be Maxwell wave equation, and that's the topic of next slide. Here the changes are, you remember we're talking about position changes and time changes. The changes are not due to Newton's second law, the changes are due to the following. Faraday's law says that curl of E, curl is curl is the position change of E is proportional to changing magnetic field, and here changing means time change. And Ampere's law talks about curl of B, magnetic field position change, as proportional to something that maybe students some do not know, some students do not know, and that is what I said as an optional topic, that is proportional to current, and that's called displacement current, the time changing electric field. Now if you start again a discussion about the first equation, and you take position change of both sides of first equation, here position change of position change, that's a second derivative with respect to position. Now here you go to position change will be of B, magnetic field, and that is given by this second equation. Now this will become eventually second time rate of change of electric field. Mathematical details I have to skip. Now the differential equation, you can hopefully you can see that mathematical form is same as the last slide, although that was the Newton's equations, result of Newton's equation, and that is Maxwell equation. But you see same, you have second time derivative and second position derivative. Differential equations are same, and there is a similar differential equation for magnetic field. If you start from here and then start from second equation and then go to first equation. Anyway, the topic is, since differential equation are same, so solution is also same sign and exponential as I explained before. And if you want to picturize it, see the motion, and here it's a changing here electric and magnetic field, not any Newtonian force. It's electric and magnetic field what changes, and that produces change in the other, and so on, and the system is sustained, and that is called electromagnetic waves. And waves will describe, can you remember? It's photons, I said. How? That's next topic. But first summarize it, what we have learned so far. If the dot is reported to have zero electric charge and zero rest mass, you say dot is due to photon. Dot is due to photon. And you choose differential equation as Maxwell equations, Maxwell wave equation, and the solution are called electromagnetic field. And then if the dot is reported by electronics to have to deposit negative electric charge in the circuit, and the mass is hopefully you can recognize what is this. If this is a dot, we say this is due to electron. And the differential equation is Schrodinger equation, which is later toward the middle of the course, and this solution of that differential equation is called psi. If it is function of position time both, that's a capital psi. It's a more usually wave function is the name for psi, although electromagnetic field are also wave function. So what you have to do is, when you have found a wave function, next is you have to predict probability. But there's a problem. Wave function is a solution of differential equation that can be negative, and in general that can be even complex. But the probability density has to be positive and the real and non-negative. So what can be the relation? If you have a little experience with complex number, then you can see a relation, a solution, which is that if you have a complex variable or constant, whatever it is, you take a complex conjugate. If it is a plus iota b, complex conjugate is a minus iota b. You multiply any complex number with this complex conjugate, the result is non-negative real as probability density can be. So that means you can get from the solution of differential equation probability density. Now that is a postulates of quantum mechanics, and the book I followed for assignments etc, namely Quantum Mechanics by Zetley, that has 5 postulates, and the fourth is this: the probability density is a function, is called modulus square. So the next is question is, are we able to make a prediction? And the answer is one more task to be done. Sorry, before that I remind you, if it is dot is not due to electron, is dot is due to photon, then the wave functions are electromagnetic field, and then in that case you have to square both electric and magnetic field, and then you get probability density. Sorry, I forgot, and I said I have completed it. And now go back to what I was talking about before saying this, and that was that, are we able to make a prediction? Is our scheme complete or not? And the answer is, there's one step more, and that is that probability is sorry, that's the next slide. The probability is an integral of probability density. But before that, something else also has appeared, and we learned that, and then we come to what I've said, that how to get probability. But before that, let me answer that question. Then what is the conclusion? What we have said about photon, we have said electron or the particle or the wave. And I've answered it. And the answer is the following. Maybe electron, maybe photon, they are wave, but it's not a water wave. They are probability wave. The difference between water wave and probability wave is that if you have a detector which is a quarter of the wave, like here, then quarter of the energy will be deposited. But if it is wave is electron or photon, then photon and electron properties are never divided. So minus 1.6 times minus 1.6 charge of electron minus 1.6 times minus 19 coulomb. That is no quarter of that. That's quanta. That's a discrete. So what is divided? That is divided it. Can you guess? You have a few moments to think. I don't have more time. What is divided in quantum mechanics? What is divided is the wave carries what? Probability. Probability is divided. Now, so for example, if you have a detector here, is a quarter. So quarter of wave, but it's a quarter of probability wave. So this is a quarter of probability. That is deposit. The probability is 1/4, not dot properties. Now I come back to what I started talking about here before the slide, and that is the question is the word probability appears here, and so far I have been talking about probability density. What's the relation? That's the last topic I do, and then I finish. And that is that if probability number is a number, in certain cases probability density, what I've been talking about in this first half of this lecture is the probability density can be a function of x and y, but the function can be a constant. If the probability density is a number, so your number problem is simple so far. Probability density is probability per unit length multiplied with length is a probability. So the number so far is a number, but this thing is extendable even if, as I start a general case with this video, that this is a function of position. In general, if it is a function of position, this product will become an integral. So probability will be given by an integral, and the integral of probability density is a function square, nothing new. If it is a photon, it's electric field square. Maybe a new question is what are limits of integration, and the answer is that if you have a detector, start from A, ends at B, then integration limits are A to B. And geometrically you can say that this calculus can be described this way. This integration is area under this curve. Now I tell you what is the thumbnail of this video, and that is for a case if a detector is in 2 dimensional, it's a kind of rectangle, and in that case integral will be a double integral, either x and y. So that's it. I summarize the 4 steps in the conclusion, but you can see that as when steps are done, net result is a probability, that's a number, and then is the next slide, next video topic is how to measure probability. But if it is measurable, we have made a prediction completely through quantum mechanics. So first I summarize it, what is the scheme, and then I discuss if it is to discuss more. And the summary is what I showed you a few slides back anyway. And that is that, there are 4 steps. First, see dot properties. Choose what is the particle. If it is a photon, choose Maxwell equation and solve it. If it is electrons, because of these, solve Schrodinger equation, wave function, and then square it to get probability density, and then integrate to get probability. And probability is a number, and number is a prediction of quantum mechanics. We have made prediction. Is that quantum mechanics scheme, complete scheme? Is that all quantum mechanics has to do? For that, you have to be patient. Answer, I cannot tell answer because today's time is finished. So hopefully you will join me in the next, although answer to that question, completeness or not, is in the 5th and 6th lecture, and hopefully you will remain aware of that through subscribing this channel, and you reach 4th and 5th and 6th. That's it in this lecture.